Hello, so what I want to do today is kind of give you guys a little bit of a snapshot into chapter 22. 22 covers things like the ultrasonic sensor and buttons and the whisker boards. It's basically about digital input or digital devices. And I've set up a little robot here. It's got a couple of digital devices on it, and I'm going to kind of go through it quickly. And if time allows, I'll even do a couple demonstrations on just an Uno here so that you guys who are stuck in faraway places and don't have your teensy, you can do a little few experiments with something as simple as an Uno. But let's just get started with it. So right now I've got a button right here, just like the one you guys probably have, hooked up to a digital pin. Now mind you, the teensy, only these pins over here are pure digital plus 13. The rest of these are analog or digital. Okay? So therefore, I could actually put this on the analog side, but I'm going to keep that available for analog sensors. So I have intentionally put it over here on the pure digital side because I don't think we're going to have a lot of digital devices. Alright? And the power is on, okay, on both the main bus and on this bus, and I'm running it at 5 volts. So I'm currently supplying this button with 5 volts of power. Okay, so that center wire is live, and it's going to go 5 volts into this button. And if you look at this button, you'd see there's a resistor. That resistor is currently holding the pin high. All right, so right now the electrons are surging through that center wire, and they're going through that resistor, and that resistor is hooked up to the pin, the signal pin. And if the button is not pressed, all those electrons, the only path they have to escape is by going from the center wire through the resistor back into the input pin. So if I ask this thing, hey, are you high or not? Is there power or not? Yes, it's going to say it's high, because I have not given it a path to ground. I have not given it any alternative way out. When the button is depressed, that is going to connect the signal pin to ground, and that's going to allow those electrons an alternate way, an easy way out, so they don't have to go into the pin. They're going to go straight to ground. It's a much easier path. So that being said, with that sort of basic understanding that this pin is currently high as long as power is on, and the button is going to make it low, we need to set up our code. Okay, so here you can see I've set my switch pin, okay, is going to be hooked up to this pin 6. Alright, that's the one I'm going to be using. And I'm going to just go ahead and set that pin to input. So I'm going to be looking for data. So far, most of what we've done is output. But in this case, we're going to be looking for data, input. And I'm going to run in my loop a very simple program, which is calling demo1. And from demo, what I'm going to do is I'm going to be looking for that low state. Let me pull this down a little bit more. So again, normally this thing is high. All right? If the button is not depressed, those electrons are rushing through the resistor to the pin. So that pin, the input pin, is going to be high. So when I push the button, it's going to be low, and it's going to switch the state of the LED. And of course, it's going to change the text. And I've already loaded this, so you don't have to wait and see. But here you go. I push the button. The pin goes low. The light turns to red. I let up. The light goes to green. And the text says the pin goes high. Alright, so all you really need in this case is that one line of code right there. Actually, not even. This is the digital read command right here. Digital read. And what do I want to do? I want to read the state of that pin. Okay, so hopefully this was a quick introduction. Let me move on to another example, and let me pause it, and I'll be setting it up. Okay, so in this case, I'm going to do the exact same thing. Instead of having a button, I'm going to be using the whiskers, and you can see that I have mounted those on the bottom of my board like this. Okay, and I have in the globals here, I've created 2 pin or variables that'll hold those pins. The left feeler and the right feeler are going to be hooked to pins 3 and 4 right up here, and I have set those to input. Okay, so I'm looking for data in. I'm calling demo 2, and all I've done now is add another if statement so that, again, the state of these things is normally going to be high because there's a resistor on that board that's feeding that pin from the sourced electrons coming up the center bus, all right, the positive bus. So when a whisker is flipped, it's going to bring it low because it's going to give a path to ground. And that's all you see right here is a digital read. Okay, the left feeler. And you can see the left whisker has been activated and the light has turned. And then here's the right. Okay, it's been activated. We can see a text here and the light has turned. And if nothing is on contact, we get the no contact. And off it goes. Okay? So now let me set up another little demonstration and I'll be right back. Now here's something kind of cool. So the previous two examples, we were providing the switch or the whisker with power from the motherboard. But the Arduinos actually have a pretty cool feature. Actually, a lot of embedded controllers do. I can actually charge the pin internally. All right. So let's pretend this is my pin. Okay, this is pin 8 or whatever, right? So normally this is in a floating state, and if I input something into it, I can determine what's going on. If I put charge to it or if I hook it to ground, it'll be either high or low. But what I can do is inside the microprocessor, literally inside the little chip, okay, I can flip a switch and then connect that pin to power. So now this pin has a source of electrons, all right? So if I ask it whether or not it has power, you know, down here in the microprocessor side, it's going to say, well, do you have power? Yes, you've got power. You've got power coming from here through a resistor, which is attached to the pin. And unless I plug something onto it and hook that to ground, it's always going to state that that's high. So I can charge the pin from inside the microprocessor instead of outside the microprocessor with something like the resistor that you see on the switch or on the feeler boards. Okay, and that's done really simply. All right, and what I've done is I've made a little homemade switch. It's a little hard to see here. There's a wire sticking up in my ground bus. Okay, and this black wire is hooked up to ground. I actually don't even need this red one. It's just confusing things, okay? So I've got this black wire hooked up to the ground bus, and I have a little wire, like a piece of paper clip stuck out of the ground bus here. And I've got this little L-shaped wire here, which is hooked up to the red wire, which is going to pin 10, okay? So here's my homemade switch. I called it home switch. It's on pin 10. And this is different. In setup, when I want to declare the state of that pin, I'm going to use something called input underscore pull up. Pull up means I'm going to pull the pin up, make it high with an internal resistor. So input pull up turns on that internal resistor, which then makes that pin state high. I'm going to load this. I forgot to do that. And down here my code is really, really simple, but very similar to what you've already seen. I'm going to be asking the question of whether or not that pin state goes low. It's going to be switched on. And sure enough, if I make these two wires touch so that the orange wire now touches the ground bus, the switch is on, it's closed, and the light changes color. And I change my text. Okay? So now I've made a homemade switch without any soldering or any external circuits, and you can make switches out of anything: paper clips, copper wire. As a kid, I made a keyboard out of taking a metal, a soup can and cutting it into strips and sticking it on with metal thumbtacks. You can push the bent metal down to make a keyboard. Any one of a number of options, any kind of two pieces of metal that make contact, you can now turn into an electronic switch by simply using this input pull-up command here in setup. Okay, so let me get the next thing set up for you and I'll be right back. Okay, so I'm going to show you the last device here that I want to talk about is this ultrasonic. All right. Now it's a 4-wire device. It's going to need one for power, one for ground, which I've hooked up on power and ground. It's a 5-volt device, so these outer 2 pins are going to be power and ground. The inner 2 are going to be labeled trigger and echo, and you can read that on the back of the casing here to see which pin it is. Now what you need to know is an ultrasonic works by sending out a signal, which it real loud but ultrasonic, and then it bounces off a surface, and then it waits for the echo. Okay, and when the echo happens, the pin goes high, right? So it's a digital device. You pulse it, send out a loud ultrasonic scream or squeal or bang, and then it waits for the echo. And of course the speed of sound is known, so we can calculate how far something is by dealing with the speed of sound. Now, I've written some really minimal code. It is nothing to be proud of, but it's functional. It's a good test piece of code. And the code that you see in your book is much better. It's going to convert it to actual measurements we can understand. It's got some functions built in to keep it from oversampling so you don't have crashing waves. You can set the range, a whole bunch of other things which make it far superior. But I just want to see it actually work. So I have, like I said, there's 2 pins. We've got a trigger pin and an echo pin. The trigger is the one that's going to make the sound. The echo is the one that's listening for the pin, for the sound to come back. The trigger one I have to set as output because I'm going to be pulsing it to generate the sound. And the echo is the one that's going to be listening. So the trigger is output, the echo is input. And then down here, to make this thing work, I have to send out a 10 microsecond pulse. All right? And that's simply done by taking the trigger, making it high, putting a 10 microsecond delay, and then making it low. Okay, so there's our 10 microsecond pulse. Oh, and actually, I'm going to pull something up on the internet real quick, and let me pause this just for a moment. Okay, I just wanted to show you this cool new command that we're going to be learning in Arduino. It's pulse in. We're going to take advantage of something that's took a lot of work on somebody else's part to come up with a nice function for us to use. So pulse in, what it does is when you call pulse in, you tell it the pin. In this case, we're looking at the echo pin. That's one we want to listen for. And then what we want to do is we want to get the value, whether or not we're looking for high or low. And then if you want, we can set a timeout, and Chris does in the book, which is well worth it. Timeout would be, I haven't heard anything, let's just give up. Okay? The way I did it, I didn't put a timeout, so it just would sit there until it hears something. Eventually it times out, just gives up, but it's a long time. Okay? So we're going to use this function, which has already been created for us, and take advantage of it to get a value. So going back here, okay, we've sent our signal high for 10 microseconds, and then I created a variable, this value, and then I called on that function pulse in, and I'm looking for what? The echo pin. I'm looking for a signal on that pin, and I'm waiting for it to be high. Again, I didn't do a timeout here. This is a really lousy, crude, but yet functional demonstration. And then I'm simply going to display that value. And you can see it's running over here already. And so if I put my hand close, you can see that the time it takes for the echo, I should have something more solid so you don't get the erroneous stuff, but that was the time it takes for the echo to come back gets smaller. Oops, I'm getting too close. It gets smaller as I get close, and further and bigger as I get further away. So you can see it really works very well. It's just measuring the time it takes for the sound to leave one and echo back to the other. So hopefully that'll get you started on the chapter. Read it, add the code that Chris has, complete it, make something much cleaner than this, and then you'll be set to go. See ya.